In this lecture, you will learn about light detection and ranging, or LiDAR, sensors, from concepts via challenges to implementation examples. The principle behind LiDAR sensor distance measurements is quite simple. The sensor emits a short laser pulse. The time it takes for the reflection to come back is then measured. The absence of a reflection means that no object with enough reflectivity was present in the path of the laser beam. Knowing the speed of light, the distance of travel of the received pulse is easily calculated. However, there are a number of challenges to address. You will hear about a few such challenges soon, but first, more on LiDAR measurement basics, starting with a simple example. Measuring a time from emission to reception of 250 nanoseconds is the equivalent of the distance to the reflecting target of 250 times 10 to the power minus 9 times 3 times 10 to the power 8 divided by 2, which equals 37.5 meters. That is, the distance to the target is approximately 37.5 meters. There are two main types of LiDARs for automotive safety applications. The static LiDAR, which include one or more fixed LiDAR transmitters pointing laser light beams away from the vehicle. This sensor type is relatively inexpensive, but the application areas are limited by the typically very limited angular coverage of the beams. The rotating LiDAR, on the other hand, is more expensive, but much more versatile. The figure on the right shows the concept of one possible configuration of one vertical layer rotating LiDAR, a 2D LiDAR. That is, the LiDAR measures distances in one vertical plane. The yellow parts of the LiDAR are typically rotating 360 degrees, moving a mirror with it. The laser pulses from beneath measures the distance to the closest objects, although multiple reflections can be addressed. That's something you will hear about more soon. Typically, the laser transmits and acquires measurements several thousand times a second. An angular encoder is measuring the angle of rotation of each individual range measurement. The combination of range and angle provide a position relative to the vehicle, which can be expressed in Cartesian XY coordinates if needed. The resolution of range depends on the laser measurement unit, while the angular resolution is determined by how fast the mirror rotates in relation to the frequency of the laser pulse, as well as the angular resolution and precision of the angular sensor. Here is an example. 14,400 pulses a second at 10 Hz, or revolutions per second, means 0.5 degrees angular resolution, as you can see in the equation on the bottom. Here you see an example visualization of a one vertical layer LiDAR sweep from an old homemade LiDAR unit. The red dot is the own vehicle as it moves. As time goes, the vehicle is moving towards the left, making a trail of red dots. The blue dots are the LiDAR measurements plotted in global coordinates over time. That is, 20 times a second, approximately 250 data points are measured, with approximately 1 degree horizontal separation, covering approximately 190 degrees in front of the vehicle. The sensor is mounted in front of the car. The video shows each LiDAR measurement accumulated over time in global coordinates. The blue moving worms are cars, one in front of the vehicle, turning right, and a few others in the intersection that the instrumented car is approaching. In rain or snow, or when the LiDAR measures through, for example, foliage, the received laser light may be from multiple reflections over time, with different amplitudes. That is, the light bounces off multiple objects in the path, where part of the light either passes through or part of the beam slips past the object, such as pine needles in the figure, or a drop of rain. Depending on the application, choosing which of the laser light returns to use in the distance calculations may not be obvious. However, methods for dealing with multiple reflections are improving continuously by sensor developers. If only a single vertical LiDAR beam plane is used, either as a static or a 2D scanning LiDAR, any pitch of the own vehicle will change where the beam strikes. Even an only 1 degree pitch means 1.74 meter change in 100 meters. This can result in the laser light missing, for example, a leading car altogether, either hitting the ground in front of the own vehicle or passing over the vehicle in front. Note that the same calculations can be used for angular resolutions horizontally. for both static and rotating LiDARs. A LiDAR with a 1 degree angular resolution horizontally could thus miss hitting a car, at least for one individual sweep at the distances of 100 meters. This since many passenger cars are less than 1.74 meters wide. Another aspect of 2D LiDAR implementations is that the type of information received is very limited. As seen in the right figure, the shape of the vehicles can be reasonably easy to identify, but without including object motion over time, such as measuring the frequency of leg movements of a person walking, it's basically impossible to differentiate between a pole and the legs of a pedestrian. Here you instead see the same sequence, but in motion. It is easy to identify the moving vehicle, and it's even possible to see the motion of the legs and of the pedestrian and the bicyclist. Note the LiDAR shadows behind the objects. See, for example, how portions of the parked cars have missing LiDAR measurements as the car and the bicyclist passes. That is, the LiDAR can of course not pass through the solid objects, shadowing objects behind. So far, you have seen static 1D and rotating 2D LiDAR sensor concepts, corresponding to the left and middle sensors here. By adding a third degree of rotation, a 3D mapping of the world is possible. The vertical rotation can be 360 degrees, but here it typically makes more sense to sweep back and forth, optimizing useful measurements over, for example, 30 degrees vertically. Instead of having a sweep vertically, static laser beams are sometimes used at fixed angles, but it's then difficult to get the tens or hundreds of measurements over the vertical angle that is to be covered. This is an example of a 3D scanning LiDAR that currently is used in many automated vehicle development projects. You see the emitter and receiver apertures. Actually, in the last few years there has been a rapid increase in the number of LiDAR sensors with 3D scanning functionality. Here you can see the conceptual representation of how a 64-beam LiDAR from the company Velodyne can sweep the surrounding 360 degrees and produce billions of data points over time. The sensor provides millimeter measurements of the vehicle surrounding in 64 vertical layers of LiDAR measurements. The multiple LiDAR beams provide much more information than a single beam LiDAR in highlighting objects, making them recognizable and showing movements. Actually, LiDARs are currently the sensor of choice for most of the automotive industry developing automated vehicles. Here you see an example of a vehicle with a LiDAR mounted on the roof of the car, with other sensors mounted on the roof as well. As you understand, the design of vehicles including 360-degree sweeping LiDARs are likely to be somewhat different from the traditional sleek roofs, as the sensor needs to be high enough to cover areas close enough to the own vehicle. So far you have only seen virtual representations of the concept of LiDAR, except for the home-built 2D LiDAR. Now to a more state-of-the-art sensor output. This video shows what is called a point cloud. The moving black patch seen in the top view in the beginning is a LiDAR instrumented vehicle. Note that the view of the LiDAR measurement is shifted from the start into a virtual position, basically on top of the instrumented vehicle. The blue lines are individual vertical sweeps of the LiDAR. Note the LiDAR shadows behind, for example, vehicles. That is, for example, when other road users passes between the LiDAR sensor and a vehicle in front, it is then in LiDAR shadow, as it basically also is for human driver. I hope you enjoyed this lecture. There is much focus on LiDAR sensors in the automotive industry for automated vehicles and safety applications. We are likely to see major developments over the next few years, not the least in cost reductions for use in production vehicles. Who knows, we may even see LiDAR-equipped bicyclists or even pedestrians eventually.